This is the F-35B. It is a supersonic stealth fighter that can take off in 300 feet and land vertically on a ship. Every other aircraft that hovers uses rotor blades to stay airborne. The F-35B uses something that should not work at this scale, at this weight, in this environment. And understanding why it barely does is the only way to understand what it actually is. Most people who talk about the F-35B's hover capability have never stopped to ask the question that should occur to any engineer looking at the aircraft for the first time. A Harrier jump jet, the aircraft the F-35B was designed to replace, hovered by vectoring the thrust from its single engine downward through 4 rotating nozzles. The thrust came from one place and was redirected. Simple in principle, brutal in practice, but at least coherent as a mechanical concept. The F-35B weighs roughly 60,000 pounds at maximum takeoff weight, nearly twice the Harrier's weight. One engine producing vectored thrust cannot support that weight in a stable hover. The physics do not permit it. So the engineers at Lockheed Martin and Pratt & Whitney faced a problem that had no existing solution. How do you make a 60,000-pound supersonic stealth fighter hang stationary in the air? The answer they arrived at is either brilliant or insane, depending on how long you spend looking at it. Most engineers on first exposure say both. The F-35B uses a shaft-driven lift fan. Behind the cockpit, where a conventional aircraft would have an avionics bay or additional fuel capacity, the F-35B has a hole. A deliberate, structural, load-bearing hole approximately 50 inches in diameter, running vertically through the center of the aircraft. Inside this hole sits a counter-rotating lift fan, 2 sets of blades spinning in opposite directions to cancel torque, driven by a mechanical shaft connected directly to the main engine. When the pilot selects hover mode, a clutch engages and the engine begins driving the lift fan through this shaft at up to 9,000 horsepower. The fan draws air from an intake on top of the aircraft and pushes it downward through the bottom, generating approximately 20,000 pounds of lift directly beneath the cockpit. Simultaneously, the main engine rotates its rear exhaust nozzle downward to contribute its own thrust vertically. Roll control comes from jets of air bled from the engine and ducted to the wingtips and tail. The aircraft is hanging in the air supported by 3 separate thrust sources that have to be balanced continuously and precisely, or the whole system departs controlled flight immediately. You are standing on the flight deck of an amphibious assault ship. The F-35B comes in over the stern at 60 knots, decelerating. You can feel the sound before you hear it clearly. A layered, complex roar that is different from any other aircraft because it is coming from multiple airflow sources simultaneously. The lift fan intake on top of the fuselage is drawing air with enough force to lift loose equipment off the deck. The downwash from the fan and the engine nozzle combined creates a column of disturbed air that makes the aircraft shimmy visibly in its own turbulence. The pilot is making no large control inputs. The flight control computers are making thousands of small ones, adjusting fan speed, nozzle angle, and bleed air distribution 60 times per second. From the outside, it looks almost calm. Inside the cockpit, every system on the aircraft is operating at or near its thermal and mechanical limits and has been since the pilot selected hover mode approximately 90 seconds ago. Here is the fact that the aircraft's advocates do not lead with. The F-35B's lift fan is driven by a shaft that runs through the gearbox at 29,000 horsepower of peak transmission load, roughly the output of 20 Formula One engines combined, transmitted through a mechanical coupling the size of a large dinner plate. This shaft, this gearbox, and this clutch are the single most mechanically stressed components in any production aircraft currently flying. Too little torque, and the fan cannot generate sufficient lift, and the aircraft begins to sink toward the deck. Too much torque and the gearbox exceeds its thermal limits and fails, not gradually, but immediately, without warning, in a way that removes 20,000 pounds of lift from the aircraft in a fraction of a second. At 200 feet above a ship's deck, that fraction of a second is the only time the pilot has before the aircraft's altitude becomes insufficient for any recovery option that ends with the pilot alive. What happens next is the question this section is not going to answer yet. because the engineers spent 15 years arguing about it before they arrived at an answer that satisfied anyone. The lift fan solved the hover problem. What it created, in solving that problem, was a set of secondary problems that each required solutions that created further problems, in the way that truly ambitious engineering always works. Not as a clean progression from problem to solution, but as a cascade of trade-offs that never fully resolve, only become manageable. The hole in the center of the aircraft required for the lift fan is not compatible with a stealthy airframe. Stealth depends on surface continuity, on every panel meeting every other panel in a precisely controlled geometric relationship that deflects radar energy away from the receiver. A 50-inch hole in the top and bottom of the fuselage, covered by doors that open during hover operations, is a radar event. The doors, when open, present edges and cavities that scatter radar energy in ways the surrounding geometry cannot compensate for. The F-35's radar cross-section during hover mode is significantly higher than during conventional flight. The aircraft that is supposed to be invisible is, during the precise operation that makes it operationally unique, considerably more visible than it would otherwise be. This trade-off was accepted explicitly during the design process. The reasoning was that an aircraft operating in hover mode is doing so in a permissive environment, landing on a friendly ship, recovering to a friendly airfield, and does not require the same stealth performance it needs during a combat ingress at altitude. The shadow of the aircraft is this. The one thing that makes it irreplaceable also makes it temporarily into something it was designed not to be. The weight penalty of the lift fan system is approximately 3,000 pounds. 3,000 pounds that does not generate lift during conventional flight, does not carry weapons, does not hold fuel, and does not contribute to aerodynamic performance. It is dead weight for the 95% of the aircraft's operational life spent in conventional flight mode. The F-35B carries approximately 13,000 pounds of internal fuel in its standard configuration, roughly 2,000 pounds less than the F-35A, which does not have the lift fan taking up the space and weight budget that fuel tanks would otherwise occupy. Less fuel means shorter range. The F-35B has a combat radius of approximately 450 nautical miles in a typical strike configuration, meaningful but shorter than the F-35A's 590 nautical miles over the same profile. Every mile of that difference is a direct consequence of the lift fan sitting inert in the center of the aircraft during the vast majority of every mission it flies. The clutch that connects the engine to the lift fan deserves particular attention because it represents one of the hardest mechanical engineering problems in the program's development history. When the pilot selects hover mode, the clutch must engage a fan that is stationary and spin it up to operational speed against the full torque of the engine, smoothly, quickly, and without shock loading the gearbox in a way that exceeds its structural limits. The engagement has to be complete within approximately 90 seconds of mode selection. Too slow and the aircraft arrives at its landing point before the fan is generating full lift. Too fast and the torque spike during engagement exceeds the gearbox's tolerance and the coupling fails. The clutch went through multiple design iterations during development, each one failing in a different way under testing before the final design was proven through thousands of engagement cycles. The engineers who worked on it described the development period in terms that suggest it was the component they were least confident about longest, and the one that caused the most sleepless nights between the first design and the first successful carrier trial. The thermal environment inside the lift fan bay during hover operations is extreme in a way that is difficult to convey without numbers. The fan is moving approximately 1.4 million cubic feet of air per minute through a 50-inch duct. The mechanical losses in the gearbox and clutch system generate heat that has to be managed through a dedicated cooling circuit. The engine, simultaneously producing thrust through its rear nozzle, is running at power settings that push its own thermal margins. The bay temperature during a prolonged hover approaches limits that were set conservatively during design and have been revised upward through operational experience. Revised upward because the aircraft regularly operates closer to those limits than the original margins anticipated. The thermal margins are not dangerously thin, but they are thinner than the program's early documentation suggested they would be. And they are the reason hover duration is limited operationally to time windows measured in minutes rather than indefinitely. The question that was left open at the end of the first section, what happens if the lift fan fails at 200 feet, has an answer that the program's engineers arrived at after extensive analysis and that the Marine Corps accepted after extensive argument. The answer is, if the lift fan fails completely during a hover at low altitude, the pilot has between 1 and 3 seconds to initiate ejection before the aircraft's sink rate exceeds the ejection seat's ability to save them. 1 to 3 seconds is not a decision window, it is a reaction window. The pilot does not decide to eject. The pilot either ejects reflexively from training or does not eject in time. The aircraft is lost in either case. The question is only whether the pilot survives it. This was known during the design process. It was accepted as an inherent characteristic of the aircraft's operating envelope, not a flaw to be engineered away, but a boundary condition to be trained around. The ejection seat in the F-35B is the Martin Baker US-16E, a 0-0 capable seat designed to function at 0 altitude and 0 airspeed. At hover altitude and hover speed, it is within its certified envelope. A pilot who ejects at 200 feet during a lift fan failure, if they eject within the reaction window, has a survivable sequence. The seat fires, the parachute deploys at the margin of its minimum altitude, and the pilot lands on or near the ship's deck or in the water alongside. The aircraft hits the deck or the water approximately 2 seconds after the pilot leaves it. The 2-second separation is the entire safety margin between the pilot and the burning wreckage of a $100 million aircraft falling from 200 feet. The Marine Corps operates the F-35B from ships that were not designed for it. The America-class and Wasp-class amphibious assault ships that carry the F-35B were designed as helicopter carriers with a secondary fixed-wing capability inherited from the Harrier program. Their flight decks are not angled like a conventional carrier's, do not have catapults or arresting wires, and are not equipped with the firefighting infrastructure that a conventional carrier maintains for aircraft recovery emergencies. An F-35B that crashes on the deck of an America-class ship during a hover recovery is a different kind of emergency than the same crash on a Nimitz-class carrier. Because the Nimitz-class was designed with that possibility explicitly in mind, and the America-class was not. The program managers knew this. The Marine Corps accepted it. The operational reality is that the F-35B flies from ships that are doing their best to accommodate an aircraft they were not purpose-built to support, and the gap between what those ships were designed for and what the F-35B demands of them is managed through procedure, training, and the professionalism of the crews aboard, not through engineering. The pilot workload during a hover recovery has been reduced dramatically from what early simulation suggested it would be. The flight control system handles the continuous balancing of the 3 thrust sources automatically, presenting the pilot with a simplified control interface that abstracts the underlying mechanical complexity into a set of inputs that feel, deliberately, through years of software development, like a conventional aircraft landing. The pilot controls descent rate and position over the deck. The computer controls everything else. This abstraction is both the hover system's greatest achievement and its deepest shadow, because it means the pilot has limited direct awareness of the system's actual state. They feel what the computer presents to them. If the computer's presentation and the aircraft's actual condition diverge, if a sensor fails and the flight control system is working from bad data, the pilot may have no indication that the aircraft is closer to its limits than it appears to be until the moment those limits are exceeded. The F-35B program cost $55.1 billion in development, a figure so large it stops feeling real approximately 1 second after it is stated. Here is what it actually means. The United States spent enough money developing this aircraft to build and equip 43 new hospitals, or to fund NASA's entire budget for 7 consecutive years, or to buy every NFL franchise currently in existence and have money remaining. That expenditure produced an aircraft that exists in no other country's inventory, that can do things no other Western aircraft can do, and that represents the culmination of a development program that came close to cancellation at least 3 separate times for reasons that had nothing to do with whether the aircraft worked and everything to do with whether anyone could afford to continue finding out. The program's early years were characterized by a specific kind of institutional dishonesty that the Government Accountability Office documented in reports that were accurate and largely ignored. Cost estimates were presented to Congress that the program office knew were optimistic. Schedule estimates were presented that the engineers knew were unachievable. The concurrency decision, the choice to begin production of aircraft before development testing was complete, was made explicitly to maintain industrial base employment and political support in the states where the aircraft was being built, and was described internally as a risk management decision while being understood externally as a budget management decision. And aircraft were delivered to the military with known deficiencies, problems that had been identified during testing and not yet fixed, on the understanding that the fixes would be retrofitted later. Some of those retrofits took years. Some are still ongoing. None of this means the aircraft does not work. It does work. The Marine Corps declared initial operational capability for the F-35B in 2015, and the aircraft has since deployed on combat operations, flown thousands of operational hours, and accumulated a performance record that its crews describe in terms that leave no room for ambiguity about whether it is a capable combat aircraft. The hover mode works. The stealth works. The sensor fusion, the F-35's ability to integrate data from its own radar, its electronic warfare systems, its data link network, and an off-board sensors into a single coherent picture that no previous aircraft could construct, works in ways that pilots describe as changing the fundamental experience of air combat. An F-35B pilot in a hover recovery over a ship is not just landing. They are simultaneously tracking every radar contact within 200 miles, sharing that picture with every other aircraft and ship in the battle group, and managing a sensor suite that cost more to develop than the entire GDP of several nations. The human beings who fly the F-35B are not unaware of the shadow beneath the persona. They know the lift fan's thermal margins. They know the reaction window during a low-altitude fan failure. They know the gap between what the ships they fly from were designed for and what they are being asked to do. They fly it anyway. Not from ignorance, but from the same calculation that every military aviator makes about every aircraft they strap into. The mission the aircraft enables is worth the risk the aircraft imposes. That calculation has been made incorrectly before, by pilots and program managers and acquisition officials who were wrong about the risk or wrong about the mission or wrong about both. The F-35B's record suggests the calculation has not been made incorrectly here. But the record is still being written, and the aircraft is still being improved, and the thermal margins in the lift fan bay are still being revised, and the clutch design that took 15 years to get right is still accumulating operational cycles that no test program fully anticipated. The F-35B can take off in 300 feet from a ship that was not designed for it, fly supersonic to a target defended by systems that cannot see it coming, and return to hover over a deck the size of a parking lot while managing the most complex sensor picture in the history of tactical aviation. It can do all of this because a 50-inch hole was cut through the center of a stealth airframe and filled with a fan driven by a shaft loaded to 29,000 horsepower through a clutch that took 15 years to design correctly. The hover works because the engineers refused to accept that the physics would not permit it, and kept working until they found the version of the physics that would. The shadow is that the version they found requires everything to work simultaneously, perfectly, within thermal and mechanical margins that leave the pilot between 1 and 3 seconds to act if it doesn't. The persona is that in thousands of operational sorties, it has. Both of those things are true at the same time. They will remain true at the same time for as long as the aircraft flies, and understanding that both are true simultaneously is the only way to understand what the F-35B actually is. 5B actually is. 5B actually is.